Okay, so welcome back. Now we do a little bit more of the theory of SGD. And just as a warning, the honeymoon period is over. So the first three lectures were like basics. Now we're ramping it up a notch. Let me know if anything goes too quick. But we actually have a quite packed agenda for this one because I think we're all burning to find out what actually happened in this example that we looked at with the SGD. So the modern understanding of SGD is really what we want to look at, and that sort of has the implicit regularization, but it goes so weighted measures goes beyond convergence, because convergence is like a necessary thing that is maybe good to have, but to really understand what SGD is doing, we need to talk about implicit regularization, the structure of the optimization landscape, especially how it relates to the width of the network and number of parameters, and then also what these things do in continuous time, and maybe then do the same thing we did yesterday. Remember when we went to continuous time to neural ODEs to analyze things, get some insights, but then actually we realized we're not going to go back to square one. So we'll actually use this thing called a backward error analysis, a common tool in numerical analysis, to see what this continuous actually can teach us about the discrete that we're looking at. Because in the end of the day, everything is going to be discrete. So that's what we're aiming for. And the key observation from earlier in the break, before the break, was that this quote unquote lazy regime, it's actually a technical term, it's not a slur or so, it's the lazy regime. So you make the network really, really big, works surprisingly well. And that's something we want to understand. So why is that the case? And first of all, we will talk a little bit about the geometry of the landscape. Then we'll talk about regularization in continuous time, go back to finite time, and then we'll go really wide. This is sort of the key outline. Okay, so the first thing that, to be honest with you, is more of an empirical observation at this point. I couldn't really find a really proof for it, but it is a debate that is also pretty hot about sharp and flat minimas. So if you are at a local minima or minimum theta star, and you look at the Hessian of your empirical loss function, of your expected loss function, let's say you can have it, and you look at the spectrum, then you could think about a minimum that is sharp by if the largest eigenvalue is really big. What? Huh? Why not the small? Yeah, good question. Because this would mean if lambda max is very big, there is one direction along which the loss function really, really is sensitive to small changes. If the lambda is very small, then okay, you hitting at ill conditioning, that's not so big of a trouble, because like in that direction, like you're not very sensitive to the actual choice of the weights. So what you worry about is the lambda max, but I think usually I would actually also look at the ratio, because you can always scale everything by 10 to make it bigger, right? But yeah, the lambda max, like if you have a direction where the objective function is very sensitive to, then we would call that sharper than if they would all be flat, as a flat objective function, so all of the directions, you're not so sensitive. It doesn't matter if you quantize your weights or if you maybe resample a different batch. So that's a hand-waving argument that maybe these minimizers could be appealing because they are like easier to encode. So the hypothesis is that, and it's based on empirical evidence, that these flat minima correlate with a better test error. Okay. And the sharp minima is what usually indicates some overfitting. And yeah, it's it goes back to a paper from 2017, which actually has been hotly debated since. And maybe as you realize, and I'll show you real quick, is you can make this any minimizer arbitrarily sharp or flat. How do you do that? So what you do is you pick a theta prime here, let's say. You just do a diagonal scaling to your original theta, and get those weights here appropriately. And in the end of the day, you're not changing the problem. So you're scaling, and then actually in the loss function, you undo the scaling, and in some sense, everything cancels out, and you're done. So you can always like change units, if you will, to make something less sharp. So clearly, sort of this simple definition of the loss of the Hessian needs to have some adaptation. As a counter argument, you would say, you always need to study this in terms of the optimization as well. So maybe in this scaled coordinate system, you wouldn't even have converged to this sharp minimum. So anyway, so it's a bit of a trouble. But generally speaking, flat minima is what everyone is after. So measuring this curvature is a bit hard because we saw that this simple parameter rescaling can get you into trouble here. So what people are actually more interested in is using parameter independent metrics. And one thing that will come up is called the Fisher information, which in some sense really just teaches you what is not what are the parameters of the model, but how does the output change. So the output of that model is something that is like the predicted label, and you can study sort of the curvature in those predictions. So this is how this would look like. It's more recent, relatively recent work about the geometric sharpness. And the way you do this is sort of you have the gradients of the single loss functions for a single data point, but then you have the inverse of the Fisher matrix, which basically you can think about it as a J transpose J from the Gauss-Newton. And now if you do the if you repeated this diagonal scaling example, so if you scaled all your weights at your model, then each of the derivatives would always get you a factor of d. And because you're taking the inverse here, they would all cancel out. So then this is one way to be more parameter independent, and it's supposedly a better measure of sharpness. We're not going to really measure sharpness today, but if you ever wanted to, this would be a better idea to use. Okay. Yeah, Liz?
Generalized Gaussian, you had a hashing mean
Yeah.
you're not include the Fisher.
Not in the Fisher matrix. There, actually, one thing you would do is you would include the logit in the model. Yeah. So and what that boils down to is basically you have a rank 1 approximation of the Hessian. Yeah. Excellent question. So, so you want to look at this matrix and then the largest eigenvalue. Yeah. Okay, good. Cool. So now take a leap of faith. If we want to get flat minimizers, then we can do some theory why SGD may go to flat minimizers and in which situations. Okay, so let's do the first thing first. Let's take a look at SGD in the continuous limit, by which we now mean we take an infinitely small learning rate. So this is not a neural ODE type of thing where we look actually at the network structure. We're looking at how do the weights change, and they may follow a curve too. So here's some review about gradient flow. So let's think about a very simple problem where you actually have maybe even a deterministic loss function. So don't think about an expected loss, and you think about the gradient flow as a limit of gradient descent. No noise, no nothing. Okay. So think about a linear model, for example. That's actually the cleanest case. So what happens if you start your weights all at 0 and do a gradient flow on a linear problem, linear least squares problem? See, that's something well known in linear inverse problems, that you have a time-dependent regularizer. So theta at time t, where t sort of is sort of similar to an iteration index now, is actually the argument of the least squares problem with a regularization of 1 over t. Okay, so what is, does that make sense? Probably, because when t is close to 0, your weights will be very, very small. Okay, so you will actually be staying close to 0. And when t becomes large, the influence of the regularizer goes, and you'll actually converge to a solution of that linear system. Yeah?
To the previous point, as so I'm sure someone has done this because machine learning, everything has been done. Did people look at this in a more strategic way, right? So you can, Fisher information comes up with optimal design, right? So you have an alternate loop kind of structure. Is that something people have done? Or is it just you optimize, you check, you realize, well, this is not flat, let's keep going, or do you do a restart?
Good question.
I don't know.
So basically you're asking, has this goal been explicitly encoded?
That's right.
Yeah. To some extent, we'll see later, but not directly. So okay. Okay. Sorry? Yeah, so eta goes to 0, so then these are close together, and then you sort of discretize, or you really, let's say you really solve this equation, then this will be sort of where you are at time t. Yeah, so yeah, think about eta becoming 0 and studying that continuous limit for now. Okay, good. Asymptotically, again, what I said is basically you think about this loss here being minimized solely, and you have more structure because you basically converge to the minimum norm solution. So you have you get basically the smallest theta that can get the data fit. Or probably I should have said that this is like a solution to the normal equations if it's inconsistent. Let's say it's consistent for now. Okay. So the gradient flow would actually select a minimum norm solution, or at least closest to the initialization. These are regularization properties, right? So this is something that is encoded and that we know for linear inverse problems that we can build up on. Okay, now we don't look at AX equal to B. We have nonlinear functions, we have neural networks. We don't know sort of what is the complexity measure. There are, though, some works. So if you go into this branch of the literature, you'll find some similar results and proofs for things like linear networks. So this take a network and remove the activation functions, which may sound weird, but okay, that's something people are interested in because you can actually do some analysis, and there are some ties to like low rank and low tensor rank factorizations. But this is sort of for linear least squares, it's a very clean analysis, and so we can use this sort of as a guiding principle for now. And there are extensions. And then if you do early stopping, then you have implicit regularization and basically a tendency to have quote unquote simple solutions. By simple we mean small L2 norm. Okay. But we don't really have a gradient flow, have we? We have an SGD. So if we want to relate this to something called a stochastic gradient flow, we need to remember one thing that we sort of said we can believe in if the batch size is large enough, namely that we get an unbiased estimate of the actual gradient plus some noise. And that noise is normally distributed here in our case, okay? So this is an SDE. And it's actually not just any SDE, it's actually like a Langevin dynamics because you have a gradient of the loss function here. Okay, so that could be good now to think about as a continuous limit of an SGD for a very small learning rate. Again, under the assumptions that there's no heavy tails, but we'll do that simplification for now. So then here is the SDE that we may be interested in. So we have a drift term. We drift toward minimizing this loss function or stationary points thereof. And then we have a noise term. And that noise term depends sort of inversely proportionally on the batch size. And then some properties of the actual loss function, like the noise in the loss function. Okay. And if there's no noise, this is the same as a gradient flow. So it's a true extension. Okay, so now there are some results, again, for simple architectures and least squares, or actually linear least squares in this case, where now, so this is a stochastic differential equation. We cannot really look at this trajectory-wise. We need to think about this as a generator. But if you sort of sampled a few trajectories and took an expected value, then these should be about the gradient flow trajectory. So you add noise in there. And therefore, you can say that the SGF, in this case, also in expectation, has the same regularization properties as the gradient flow. This is how the argument that goes. And yeah, then as t goes to infinity, we'll take a look. But there was a question there, yeah. Yeah, that's sort of like the diffusion coefficient. Yeah, I mean, pretty much, that's the standard way of sampling, right? So you have the psi t that are normally distributed with the identity covariance, and then you have your scaling there. So the dWt is just the standard Brownian motion, and then you have your diffusion coefficient. Okay, good. So if we go for t equal to infinity, we could think about what is sort of, I mean, we at time 0 we initialize the weights randomly. So theta 0 comes from some distribution. And now we could think about, okay, if we let this run forever, what would be the distribution of those weights? Okay, let's take a look. As a reminder, I think this will be our daily reminder, the Feynman-Katz formula. Because what does that allow us to do? It allows us to kind of, in some sense, switch everything being regular between SDEs and PDEs. And for our case, this looks like so. So if we have an SDE like this, which we have, where G is just the gradient of the loss, then the density of the weights follows this Fokker-Planck equation. This is a Fokker-Planck PD. You have a drift term and you have a diffusion term. Okay, and that's pretty cool. So it's a high-dimensional Fokker-Planck equation. Dimension, what was it? I don't know, 50,000 or something like that. But that is one way you can study this. So now if we look at a Fokker-Planck equation, and maybe let's make an assumption that the diffusion, the covariance matrix of your mini batch noise is just a scalar multiple of the identity, just to keep it fit on one slide. Then you can actually have nice results, because then you get a very simple forward process. You plug this into the Fokker-Planck equation, and then at an equilibrium, this flux here must be 0. So you actually see that the gradient term must satisfy this equation, which you can sort of reverse engineer. So if the gradient of P is minus 2 over epsilon times the gradient of the loss times P, then maybe you can double check that this must be written as something like a Gibbs distribution. Yep.
So I'm a little confused with terminology. Have a Langevin equation, have a Fokker-Planck equation, and then what is Feynman-Katz relation?
Well, yeah, well, Feynman-Katz allows you to change in between them.
Okay, so it's Feynman-Katz isn't an equation.
It's a formula. It's a theory. Yeah, it's a transform that allows you to do this. And this exchange here is not arbitrary. So the G basically ends up as your advection coefficient. And then with the diffusion coefficients, there's always this thing that you need to go from square root 2D to just D. So it's not an arbitrary exchange, but and it always goes this way, and then the opposite way you need some regularity. But it's a mechanism to switch from an SDE to a high-dimensional PDE. And if you like PDEs, then we can study that PDE to understand what the SDE is doing without too much stochastic processing. But anyway, so what we have seen here, this is really the highlight, is that the distribution of the weights in the asymptotic limit follow some distribution where the energy depends on the actual loss function divided by epsilon. And epsilon, defined here, is the ratio between the learning rate and the batch size. So what does that buy us? So this again is the result. You can think about the epsilon being the temperature. And if you know about Gibbs distributions, this is like an energy-based model. That temperature, so if epsilon goes to 0, let's say, this becomes very sharp at the minimizers of L. But if the temperature is very high, you actually smooth this out. Right? So this means then that the distribution, let's say for a large learning rate, that distribution would be expected to be more spread out. So you would explore more. Whereas for a small temperature, you would really zoom in on minimizers. It's sort of not a too clean argument, I admit, because in the beginning we said theta, like eta would be 0. But okay. Sometimes that's how it is. And the same with the batch size. So if you reduce the batch size, then you basically flat out the distribution a little bit more. So you'll bounce around much more than you would with a very large batch size. And that is something people have trained in a network with SGD that you should have seen. And there's also like this, the other thing I will say is that this temperature, so since the temperature is eta over B, there are these usual quote unquote scaling laws that when you double your batch size, you also double the learning rate. Engineering type thinking, but usually that's actually how they do this. So then you would actually keep the asymptotic distribution invariant. Yeah. Again, like small epsilon near global minimizers or local minimizers really, and large you explore more, and hopefully you would find flatter minima, so they would actually smooth out also. Okay, so then in some sense we've learned that we have some implicit bias and that we have control over the sampling with the SGD. Okay, but there is one catch. Namely, in reality, we will not have a step size of 0. And surprisingly, actually, there are some again, this is an empirical observation, that you want to be really living on the edge. So if you know from gradient flow, if you discretize it with gradient descent, you have sort of a step, which is a forward Euler method. You have a stability radius, and that gives you a condition on how large your learning rate should be. If you knew lambda max of h. But in principle, there's this condition, right? And usually in numerical analysis, we would say, well, this is the maximum you should go, but to be safe, let's just have a smaller value. But it turns out that for gradient descent, what people have observed is that where you actually want to be with your step size is you really want to be approximately on the edge. And then there are some ways people think about explaining this. They think, for example, about that if you have this ability to take large steps whenever you incur a large gradient, then maybe you get out of points you don't want to be in. But this is empirical. But what goes without saying is that in practice, eta will not go to 0. So that's something we've got to account for. So what do we do with finite step size SGD? Surprisingly, there is something we can do, and that maybe goes into the direction of Andreas's question. Okay, so basically, if we believe that finite step sizes are important, then we should admit that if we do gradient descent, that is not the same thing as solving a gradient flow. Okay, but how about this? How about could we find a modified loss function, not the original loss function we're asked to optimize, but maybe we construct it as a different loss function so that our discrete iterates are on the gradient flow for that loss. What is this line of thinking called in numerical analysis? So you have a discrete algorithm that is supposed to solve a continuous problem, but now you're actually asking which continuous problem does it actually, yeah? Backward error analysis. Yeah, you try to find the continuous problem that this discrete thing actually follows. Okay, so this is how this looks like in a picture point of view. So these are, this is just some arbitrary objective function. You start here, you do your black dots are the gradient descent steps, and the blue is the actual gradient flow of that loss. So now you say, okay, so what do I need to, how do I change my loss so that the gradient flow gives me this red curve and that all my iterates are on the trajectory? Does the goal make sense? No, the goal then is to, first of all, construct this modified loss and maybe reveal some structure. Maybe we learn, okay, if we added this term, then we would be happy, and maybe that term is the reason why being on this edge of stability, having finite step sizes, leads us to generalization. So hopefully, first order of business, let's construct a modified loss. And the second order of business is maybe we learn something about why this discrete optimization method actually can work. Yeah?
Here, if your loss modified function is close to the original loss function.
I don't know. I don't mind at this point, but maybe we shouldn't think too far. Like usually in backward error analysis, actually you would care, you would want to be close. So let's maybe stay with that. Okay, good. Then let's keep going. So how do you do this? So let's say we have our discrete iterates. They are approximately along some curve, and we can do a Taylor expansion, just as we always do. Then you take this Taylor expansion and you set it equal to this discrete update. Something we can do. We cancel the common terms. And so you see the derivative terms of the Taylor surviving and the step from the gradient descent. And now in some sense, you can rearrange it. So you have some ODE, which is now a second order ODE, seems like it, with that drift term. Just some calculus, okay. Now we need to do this reverse type of thinking. We want to find the modified loss so that the gradient flow will be equal to that. So let's say we have this modified loss and we compute second order derivative of this for our Taylor term, and we would realize that this would be sort of the Hessian of the loss times the time derivative of the weights, and this one we know. So this one we would hope would be something like the gradient, because we have made that assumption here. So again, so we're deriving this, and now comes the observation, and we can double check that this is the case. If we modified the loss, we took the original loss plus eta over 4 times the norm of the gradient squared, then taking the gradient of this would actually be the gradient of the original loss plus eta over 2 times the Hessian of the loss times this plus like a term that we can sweep under the rug. And now we need to do some comparisons. I'm standing very close to this, but if I'm looking correctly, then we have this term here, which is basically the second derivative here. And now with the eta over 2 goes into the Taylor expansion that we've seen before. Okay? So what we've seen is this modification, after ignoring the second order term, because we do the usual approximation, will be our modified loss function. Or will be a modified loss function. There are probably many. And we stayed close. I mean, relatively close, depending on the step size. Okay. And that I find interesting, because now I think your head starts thinking, Andreas. So now you can ask yourself, okay, so what actually happens if I had this term in my objective function to begin with? So let's screw the loss, let's add this thing and add it. So this is the modified loss breakdown. So you have the usual training loss, but then you have this penalty. And what does this actually do is, of course, we should also say at the minimizer, or a minimizer is not adding any bias, right? Because it's a stationary point anyway. far away, sure, it will actually be different. And in some sense, you can now see that the discrete gradient descent prefers regions where the gradient is relatively small, and that usually is the case in flatter regions. Because we will sometimes bounce around, and if you are at a steep decline, this stuff is really going to scream at you. And the inference of that term scales with the step size. The gradient descent with larger steps has more of a regularization effect in that case, in that sense. Okay. Yeah, so the larger the learning rate, so to say, the stronger is this implicit regularization. Because it's implicit, I should say that too, because in the end of the, mostly people minimize this thing. They don't even compute this gradient penalty. It's there because we've learned this from the backward error analysis. It's implicit. That's but it's part of like making this implicit regularizer expose it, so now we can look at it. I found that pretty cool. Really nice use of numerical math. So the finite step size then is really a feature, not a bug. Yeah.
Let's say in our first iterate, if our loss is really unstable where our gradients are exploding.
Oh yeah, then you're in trouble.
Yeah, at that time then that.
Yeah, if your gradient explodes, you're in trouble, period. This is maybe not helping you. So you want to be, of course, in a regime where you just can compute this. It may be large, but then maybe the hope is that this would get you out of there quite quickly. It would not just minimize the objective function, but also minimize the slope. Yeah?
In practice, you want penalty to the gradient is small in the beginning with a larger at the end.
Wait.
Penalty to the gradient penalty that theta over there, for the slope function to not basically settle down at a flat minimum immediately start learning. Want that theta to be small at the beginning and large at the end.
I don't know. We can maybe talk about this offline because I think I would do this the opposite way.
Yeah, then now whatever the closer solution that you can find.
Yeah, because usually the learning rate would be large in the beginning and small in the end. Yes. Yeah, that's like usually learning rates decay. So the beginning you would explore more and then you would hone in. Okay.
This would, I think, have the opposite effect. Because the penalty will be larger in the beginning. Larger.
Yeah, and larger penalty means more preference for flat regions. Well, if you settle down in a flat region, I think you would be fine. Yeah? Huh. Excellent question. So first of all, it's a theoretical argument that now explains to us why we observe certain things with gradient descent. Because you don't need to minimize this to get this benefit. You just pick a finite step size and that's what happens. Of course, the interesting question is then, so what happened if I actually explicitly regularize this? So I'm going from implicit regularization to explicit regularization. And people have shown that in the examples they looked at, this reduces the minimization gap for SAA methods. That I think was one of the questions too. Like if we have an SAA method and we're not happy with that overfitting, maybe there's some hope to add an explicit regularizer to reduce that overfitting. And there are exactly papers like that, where you look at a full batch gradient descent, which is not supposed to generalize very well, and you add this term, and you actually do see the gap sharpening. I think I have it in the references, otherwise ask me. But, and this is different from a weight decay. I should also just remind everyone. Probably a more informed version of that. Yeah?
So with this, for the discrete algorithm, it was gradient descent with big step size. Okay, so what you have is gradient descent with a big step size that gets you a steep in the points. You're trying to find the continuous dynamic that gives you that steep with the points.
Yeah.
What if you have gradient descent with learning weight schedule
Yeah.
And you did this analysis like that.
I think you would do this sort of stepwise.
Okay.
But really also now this, ideas are spinning in our heads. The benefit of having this modified loss function is, gradient descent can be slow, right? So maybe now that I have this continuous problem, I can come up with a better way to follow that trajectory, but still get the benefits of regularization from finite step size gradient descent. And that's exactly this idea of adding this explicitly as regularized. Okay, cool. We need to face reality though again. We have a stochastic gradient descent. So let's just do some mental accounting for that now that we've understood sort of what qualitatively result we are getting. Doing our usual crime that we say we are in the central limit theorem limit or scenario, have a discrete SGD. The noise is isotropic, just to keep it simple. That's a homework problem too, to make this more general. And then basically the results sort of you would be getting is you have a modified loss that still looks the same, but then again has like terms that come in from this SDE analysis that depend on the usual suspect is our epsilon, that's our temperature term, and then something that is second order in the step size, which you will sweep under the rug. But this is, I think, just to give you a taste, it's a bit more tricky because now if you actually read these papers that you need to think about things you don't try to think about, like reshuffling the batches versus not reshuffling the batches, and how you exactly randomize the SGD dynamics, and you have the assumption of the central limit theorem. But qualitatively, the results look pretty similar. And then you can play this game to think what happens with large batch sizes, what happens with small batch sizes, and play these numbers. This extra term here, that is again this goal of adding some exploration. So SGD does two things. So it has this preference for flatness from the finite step size, and then it has this exploration coming in from the gradient approximation. And so that may explain why sometimes these things generalize actually quite well. Implicit bias to simple solutions, flatness plus exploration. Because if these things, especially with this extra hidden penalty, now let's actually do some thinking. So now that we know that we have this gradient penalty, and SGD bounces around. So now if you are near a sharp minimum, you would expect at some point to go into one of these bad directions, and this thing really popping up and firing. And that amplifies this preference of getting out of there. So that's sort of again, halfway between empirical findings in like real networks versus some theory that you can actually do for simplified settings. Okay. Yeah. And sort of is in line with the other. Yeah.
So if data is really, really large,
yes.
So would the eta square be the dominant term? Are we having a different quantified method?
Well, so then I think you need to do some accounting, but also you will probably not be stable. I mean, remember there's like this is like an explicit Euler method. So there is sort of an upper limit, unless of course you go back to the way of doing an explicit regularizer, then you can crank up that weight as much as you like. But yeah, usually you're interested in finite, but small. Okay. Cool. So what I want you to take away is like these finite step sizes, we should treat them really as a feature and not as a bug. And then it's actually really interesting to look under the hood. And again, if you really try to, so by the way, the papers I mentioned, so if they actually minimize this with an SAA method, it reduced the generalization gap, but of course it's computationally expensive. So now what does your backprop brains need to do? You need to compute the gradient of this thing, which means that you have one more Hessian Matvec coming from this term. And these tend to be expensive, but not undoable. So you can think. Okay. Final piece to the puzzle. is over-parameterization, which we haven't talked about yet. I mean, these are, we didn't really make any assumptions about the network. Okay, so how does that one go? I mean, if you haven't heard, GPT-3 has quite a few weights, like a few billion parameters. And even our little Gauss-Newton example had many more weights and data points. So it seems that these things are kind of happening. I think this is an outdated, I should have updated this because we went all the way to 8,000 something and definitely exceeded the training data. Okay, so if you have more parameters than data points, then we would assume that this gives us some catastrophic overfitting, but we've learned about the double descent. So that is not really a big problem. But we don't really know yet why SGD would find good weights. So let's break this down. Since we are friends of Gauss-Newton, we can recruit this line of thinking one more time. So we have a network. We want to find, let's say we really want to do interpolation. So we really want to find a theta star so that you exactly match all of the training data. Okay. If we could find one, and just to make that clear, so I have the big X and the big Y now. And that's all your training data. Concatenated if you like. Actually, it would be more convenient to represent it as a tensor. I will admit this. But, let's think about matrices and vectors. So if you had such a pair, I mean, we could in principle think about this. We could linearize about some theta 0, just as we did in Gauss-Newton. So we have an F, we have a Jacobian, we have the delta. So this is sort of the step that gets us from that theta 0 to theta star. And we have the second order term, which I believe you evaluate at theta tilde, which is someplace between theta 0 and theta star. Classical Taylor expansion. Okay. And now wouldn't it be nice, we talked about the convexity part earlier, wouldn't it be nice if we could just ignore this term here? Quadratic term. We have cross entropy loss is convex, we have least squares loss is convex. It would be really nice if we could convince ourselves that maybe we can drop it. And the sort of the direction I'm headed is, if the network is wide enough, I want to make a case that we shouldn't worry about that term. Just leave it out, and then we have a simple problem to solve, and we will interpolate the data. Okay, so let's set this up. So let's do a squared loss function, not a log sum x, just for simplicity. And let's just assume the quadratic term can be neglected. If that's the case, then you can look at the residual at the initial guess. How bad do you, like, what's the pointwise residual of your predictions? And this would be equal to the Jacobians times the delta theta. So if you solve that with a big residual vector or tensor, then you have a linear system to be solved. And by the way, of course, if the quadratic term goes, Gauss-Newton will be there in one step. Because we have a linear least squares problem and a non-linear least squares problem. Okay, so now how do we do this? How do we design the network so that this quadratic term goes away? That's a, I don't know, $5 question. Here's a simple answer how you could do this. You take the same architecture we always had, but we importantly add this 1 over square root of n term. So we have two-layer network. So this WIs are just as before. You can use your favorite initialization. Usually you have something like a LeCun initialization is one standard candidate where you make the noise go down as you have more input features or something like that. But then the outer weights, you just pick n01, but you have this 1 over square root of n term on site. And that's sort of important because we'll play with the width of the network. The wider we make the network, the more terms you have in your sum. So clearly there must be some scaling. The square root of n may not be too obvious, but bear with me. That is maybe this an architecture that we'll take a look at. And this is actually the architecture I used in the example. Okay. Sigma is our activation function. Thanks for reminding. Yeah. So the ReLU or whatever have you.
Example.
Yeah.
You use ReLU in the example.
Yes. Okay. So why this 1 over square root of n? Let's do some thinking. So these terms are order 1 with respect to the width. Just depending on, like, the scaling here is only in the data dimension. If you sum n of these terms, then do a central limit theorem, that gives you usually the square root of n scaling in there. That would go to infinity when n becomes large. And now you basically have the answer that you say, okay, so if I multiplied every term with 1 over square root of n, central limit theorem would just kill that term, and I'd be good. Okay, so there you have it. That's why maybe it's a good proposal. Let's see what happens. So now we need to talk about some derivatives. We've pre-computed them. So if you compute the Jacobian of f for the a, so the outer weights, you have this 1 over square root of n term, and then you have your inner weights. So it's in the order of 1 over square root of n. It's about doing some back of the envelope bounds here. But that term carries through, and it also carries through when you compute the inner weights, because you multiply everything by 1 over square root of n. So in the Jacobian matrix, there are entries of size 1 over square root of n. And the Hessian of the forward model, again, this is the thing that we want to talk away, right? We want to say this one goes to 0. The mixed derivatives are 0. It's actually a block structured matrix because different data points, they don't talk to one another, which is actually also to our advantage. But the ones that do talk to one another also are in the order of 1 over square root of n. Okay. But importantly, the sizes of these blocks, so these blocks here, that's only for the weights or for the features that are close to one another, so they have a fixed size, so they don't grow. It's a block matrix in some sense. Okay. So if we have overparameterization, then if this thing will actually have full rank, at some point this will be a very wide matrix. Let's hope we can find a solution. And doing some linear algebra as we did before, formally using the representer theorem, we can construct the minimum norm solution. This one we've seen yesterday, J transpose alpha equal to R. And we can solve that. So this is the minimum norm solution for what is now called the neural tangent kernel Gram matrix. But it's really J transpose J. And it's called neural tangent kernel because it's the tangents of neural networks. But we didn't really, I mean, it's just a term, but it's a very famous term here. Just some simple linear algebra. And so then the step that we need to do from our initial guess, the one step of our Gauss-Newton that will be computed, solves with the NTK matrix and multiplies with the Jacobian transpose, and you're there. So, okay. I think one question is, and that is not obvious. So that's actually what was making this paper very worth reading, is that you would want to understand, so this K, the K matrix, so this JJ transpose, that size does not depend on the width, does it? Just the size is number of data points times number of features, independent of the width. So what is now the interesting part to study is what happens if you increase the width. Do these J transpose J's actually converge to something? And the answer is yes, they do. And they actually converge to a deterministic limit, which is an SPD matrix. So we have unique solutions. So this is sort of the dual perspective on fitting these functions. Okay, now I need to make an argument why this quadratic term goes away. Let's maybe move a bit quick here. We have this term from the Taylor expansion. We do the usual inequality to bound it into two phases, which means that we should look at what is the actual values of the entries in the Hessian versus the step size. If we can make sure that this one doesn't grow too much, and this one can go to 0, then we're in good shape. Because then we can ignore this term. First part, the parameter change is bounded, so it doesn't depend on the width. And I think that's not so long argument, but we can maybe just reveal everything first. But the interesting part is that the spectral norm of the Hessian vanishes. So this norm here, the first term will be order of 1 over square root of n. So this goes to 0, and the other one doesn't grow. So we are in business, and we can ignore this part. And how you get there is the following way. We have the minimum norm solution. We now look at the entries. So these entries in the gram matrix, there is sum over all of these parameters, and the sum only has entries of 1 over n, and in the end you'll have n of them, so that will be fixed because the number of parameters is in the order of the width. And so then when you compute these things, all these terms cancel and you're good. And for the Hessian, the important part, I think I said that, is the Hessian for all of the examples. So you have some block structures that emerge. So block sizes is fixed. The entries are 1 over square root of n. So the whole thing will be 1 over square root of n. Cool. And so now what this tells us is that this term overall goes to 0 when the width goes to infinity. So if you make it large enough, we get away with our crime of ignoring the Hessian term, because Newton should converge in one step, and the step should not be larger just because you have more neurons. So this is sort of the neural tangent kernel quick introduction to that, which tells you how to make the network wide. Yeah, for people who studied machine learning before deep networks, now this resembles really a kernel method. And basically, if you ask to do predictions at the training data, we already saw that basically we do our approximation from before. And to predict at a new point, you compute the weights here, and then you apply it based on the Jacobian. So this K here, really, you could think about a kernel as a kernel, just a generalization of a symmetric matrix in this case. So this kernel regression, by the way, here I plotted a few spectra of these kernel matrices because that's what kernel people are always interested in. This is a smaller example. I think I only had, 100 examples with 5 classes for the peaks. So this is a 500 by 500 matrix. And then I played with a number of neurons. So we have 256. So then it's clearly not full rank. It's actually rank deficient and ill-posed. Pretty bad news. But then the blue and the black, you converge to a more well-posed operator. And I thought probably if I put 32,000 weights, maybe everything will be actually much better posed. So this is sort of the thing about neural tangent kernels. And that explains the example you saw before the break, where SGD now magically worked. Because basically, what did it actually do? What does this tell us is that we didn't really learn anything. Because remember, kernel methods are a little bit out of business these days, right? Deep learning is sort of the thing in the game in town, and deep learning, the benefits is supposed to be that you learn features. And here we say, if it's wide enough, don't bother about features. Features would be these WIs, which we have never touched. We pick them at initialization and then only optimize the outer weights. So, okay, so it's very elegant and nice, and it gives some insights, but there is no feature learning. Yeah, the kernel is just fixed at some random initialization, and then you play with large numbers of numbers. And of course, infinitely wide is a big ask, especially when you need to run SGD or to solve some discrete problem. And yeah, so S is quote unquote the rich regime. So you have the small, the lazy, and in between sits the rich. That could be then worth where sort of maybe you want to have a mix of both. You want to have some feature learning, but then also you want to have sufficient width to fit everything. And there is, of course, the usual gap between theory and practice. So modern architectures show behaviors of this feature learning. We can actually look at how much do the inner weights change in the optimization. It's also interesting to look at. And yeah, how exactly to pick this sweet spot. So this is the NTK. But you can go beyond that. That's actually a second way you can think about this. That's probably the last thing we'll really have time to cover. So here, okay, the features we kept fixed, and we only trained the outer weights. Let's do the opposite. Let's do something crazy. Let's initialize these WJs, so the features randomly, but with a different scaling for some reason. And sorry, this is actually the NTK. So the other approach I want to show you, so you initialize them from N01, actually, the inner weights. And the outer weights you just pick equal to 1 or 1 over n, so that you average. No trained weights in the outer layer. You can do that. And then actually you can study all of these vectors, the weight vectors in the inside, how do they bounce around in the feature space. And then what you could think about this is like little particles, and they would go to places where there's some information, and then they produce an average prediction, and that average prediction is what's being used to classify your points. But not a smart average, like an arithmetic average. So this is the complete opposite of the NTK. But what's interesting then is that, yeah, this is how the network looks like. One hidden layer averaging outside. And this immediately, at least for some people here, for Xingjiang and Tipanshu especially, means that this is sort of like little particles or little agents. And the little agents, they try to move in a certain way to optimize some objective function. So this is actually a mean field game. And it turns out that there is a PDE on the probability space, which is the probability space of these particles. You can idealize that to another PDE. And yeah, it's called a Wasserstein gradient flow of the loss function. And then if you add noise, you don't have a conservation law, but you also have some diffusion term to it. There is a stochastic mean field game, if you will. And now you can think, okay, so does that stuff actually work? And we'll see. Yeah, and then you can prove nice theorems in the PDE sense that this should work. And for this PIX example, actually, it does pretty well. So you see almost no errors in that plot. Again, I don't know if anyone is counting, but we are in this usual like 92% test scenario where now it's probably just randomization noise. Yeah, so this is a complete opposite. And I think I like this one actually better because this one is like pure feature learning. Whereas the NTK is forget about all the features, just learn the outer weights. So two different ways to do super scaling today. Yeah, and the big difference between them is the feature learning aspects. In the mean field, yeah?
Go back. There is a fluctuation because like you stop the training and retrain it again, or
I don't know, pure noise. I don't know what it's doing. Yeah.
How do you train this?
This was Adam, 30,000 steps of Adam.
On the
On the usual cross entropy loss.
oh.
Yeah, you have the code. So if you open the code, there should be a collab. You can click on that. And I've uploaded all the config files that I found with some hyperparameter tuning. But actually, I will say for these large ones, I didn't do formal hyperparameter tuning. So that's really just you try out one parameter and then you, not graduate student descent, I use Claude descent because it actually is very good at like figuring out what numbers to pick, but it was not really in real optimization thing. It's much, much easier to find parameters that work once you are in the lazy regime, which is why if you are OpenAI and you can train one next ChatGPT model, I can see why they want to do this in the very large regime. So you can only do one run. Okay. There's a picture coming up. So what is our understanding of this SGD thing? So if we believe that we want to have flat minimizers, we've seen last time about the like unbiased gradient estimates, Robbins-Monroe conditions. Then we've seen the implicit regularization in the continuous time. You converge to minimum norm solution, small weights. In finite steps, you have this interesting extra penalty term on the norm of the gradient square that seems to reduce the generalization gap. Plus, you have the exploration from the SGD that hopefully saves you in terms of not being stuck in places you don't want to be stuck at. And then, so I think about it this way. So you have this tendency that you drive towards flat minimizers, and then the width part just ensures that you have flat minimizers to begin with. So it makes the optimization function nicer, which actually leads me also to some things that we have not covered, which is quite a lot. Okay, but yeah, I think we're ready for the picture. We pulled it off to be more or less on time. Okay, cool. We're happy to take more questions. Let me also check